hold on here. And instead of looking at Charlotte, let's instead look at a astronaut. So we have an astronaut here that has an oxygen tank and is separated somehow away from the space shuttle, or not space shuttle, but space station. What would actually be described in the picture is not what's over there on the left side. You would not basically be described what's going on. You would be told that the oxygen tank, and let's give you some information. The mass of the oxygen tank is 10 kilograms, and it was thrown with a velocity of 40 meters per second. The astronaut, which has a mass, let's say with all their gear, of 200 kilograms, they would ask you to figure out what is the final velocity of the astronaut. That's basically the description to be. And if you don't understand, okay, this is a recoil separation problem. Every recoil separation explosion type problem has a point in time where what? The astronaut was with the tank, or Charlotte was with the arrow, or the pieces of the grenade were all at one point together. So one thing I want you to, it's not always good in this to make assumptions, but in this class, if I don't describe on a worksheet whether or not the combination of these are moving, we can assume that the initial velocity of those two are not moving. Just like the rifle and the bullet, they were not moving together. So we have astronaut and we have tank. So anytime they mention, and it doesn't matter how the separation takes place. It doesn't matter if you're throwing it. It doesn't matter if it's a chemical explosion. It doesn't even matter if you have two objects that are compressed between a spring and you let them go and they separate. There is some point where they are together, and we assume that their mass is combined, and therefore their velocity is. So this being an this being a recoil explosion one, the equation which we introduced earlier would be like, okay, it's still technically this one right here, but we're realizing that what is the same between the astronaut and the tank before it is thrown. From these variables here, what is the same between the astronaut and the tank before it's thrown, or Charlotte and the spear before it's thrown? Their velocity. They are together. Whatever velocity one it is the other. So we can simplify that by just saying, okay, we'll combine their two masses together and they will have a collective initial velocity. But afterward, they'll have their own velocities. So, once again, we're given everything here except for what we're trying to figure out. I mean, if you distributed this, you would have M1VI plus M2VI, and if they had their own, but since they have their own, the collective velocity, 200 plus 10, 0. We saw this in the problem we introduced at the beginning of the chapter. We have an initial momentum of 0. That means one of the momentums on the right has to be positive and the other has to be negative. And in this case, they both have to cancel each other out. So 200 times V1F plus 10 times 40. Here we can make a prediction. This is a recoil type problem. And we're looking at this and they're not moving here. So one prediction we can make, maybe based on this, is that it's going to be a negative number. What else can we maybe predict about the size of this number? That number is going to be greater than, less than, the same as the tank. Thank you, the one person that keeps saying stuff. Less than the velocity of the tank. Zero, V1F, plus 400, and there we come to the fact that we're going to get a negative number because we have to subtract the 400 the other side, and that's where we get negative 400 equals 200 V1F. V1F equals negative 2. So we have to, before we box that, we ask, does that make any kind of sense? if you make predictions, it's a lot easier to go back and say, okay, well, that matches my prediction, makes sense. But this means that the astronaut is moving left. Okay, it originally wasn't moving, it's now moving to the left, which makes sense. It is a recoil problem. And the fact that it is 2 makes sense because it is the astronaut is more massive than the tank. And so, yes for being negative, and yes for being less than 40. Recoil type problem. Little bit of a stretch problem here. Just not. This is kind of a build on top of this. I believe we might have referred to this in the past. And I asked the question: is it possible that you could have a recoil like this, but both objects are still moving in the positive direction? So we have an explosion. Let's say we have an explosion of things, but the collective velocities of all those objects are still moving in the positive direction. Luke? Okay, so the plane would still be moving forward. The plane would be slowing down, correct? Yeah. So, So the one explanation there is you have, let's say, a plane that, let's say, its velocity, I don't know, let's say it's 100 meters per second. Okay, if it fires some kind of projectile this way, it is going to slow down a teeny bit, but it's not going to slow down less than 100 meters per second further. Another one I might have mentioned here or showed here is that in a separation between in space, we have an upper stage and we have a lower stage here. So let's say that's the upper stage, or that's the upper and that's the lower. Let's say the velocity of these is 1,000 meters per second. This is kind of interesting, of an engineering question. How do you build 2 stages of a rocket so they don't just fall apart anytime during the mission, but yet you can do something and they will separate all the time? This has been a thought process. Maybe you have clamps, but if you have any kind of mechanical design that's going on there, let me here.